Okay, so I'm going to go over some of the lab stuff today. For this week, the lab is mostly deriving some estimates for various things for these iterative methods, and that's going to involve finding eigenfunctions, finding eigenvectors and eigenvalues, and just doing some estimates using Taylor series and stuff like that. So I'm not going to do everything. I'm just going to basically give you some ideas on how to do this, and then you can proceed from there. So let's begin. Let's say A is it's an M by M Poisson matrix. Okay, so then it's going to be 2's on the diagonal, minus 1's on the upper and lowest diagonal, upper and lower diagonal, and 0 everywhere else. A very common matrix that we've been looking at. Okay, and let's look at the Jacobian. Actually, we're going to look at a few different methods. So remember, what we really need to do is, we have some sort of AX equals B, and then each iterative method is going to have a different iteration matrix. And what we need to do is we need to determine the eigenvalues and the eigenvectors. Here, most principally, the eigenvalues, and really the biggest eigenvalue in absolute value. And that's going to tell us about the convergence rate. Okay, so first thing we want to do is we want to find the eigenvalues of this matrix. We want to find the eigenvectors and eigenvalues of this matrix. Now, what turns out is that it's maybe a little bit easier to think about what the eigenvectors are first, make a guess at what the eigenvectors are, and then use that to figure out what the eigenvalues are. So if we think about what this matrix represents, so this is the second derivative. And so, what does it mean? Let me sort of write two different, ways of thinking about this. I've got AX is equal to lambda x is sort of just the linear algebra eigenvector equation. But remember, this is a discretization of a continuous thing. So if I think about what this might correspond to continuously, well, x corresponds to a function. A is going to correspond to the second derivative. So this would be something like minus u double prime is equal to lambda. I'm going to use a different one times u. Okay, and then the Poisson matrix we're looking at corresponds to the conditions u of 0 equals 0 and u of 1 is equal to 0. So we've got u of 0 equals u of 1 is equal to 0. Okay, so now the question is, maybe by understanding the eigenfunctions of this equation, it's going to help us get information about the eigenvectors of this equation. Okay, so this is a type of differential equation that you might not have seen before. This is a boundary value problem rather than an initial value problem. An initial value problem would be the differential equation plus, u of 0 is equal to something and u prime of 0 is equal to something. But notice what we have. U of 0 is equal to 0, and u of 1 is equal to 0. So it's a boundary value problem. So, okay, so if you have this, you can verify that the general solution to this differential equation is u of x is equal to C1 cosine of gamma x plus C2 square root of gamma, and C2 sine square root of gamma x. Okay, you can verify that this satisfies the differential equation. Now, to know what C1 and C2 are, it seems like we're going to have to use these boundary conditions. So if you look at x equals 0, 0 is equal to u of 0, and if we plug in x equals 0 over here, notice what happens. Sine of 0 is 0, so this term is 0. Cosine of 0 is 1, so we have C1, and it tells us C1 is equal to 0, so this goes away. Okay. What about for sine? Well, if we look at the boundary condition at 1, we're going to get 0 is equal to u of 1, and this is equal to C2 sine. Well, x is equal to 1, so we're just going to have sine of the square root of gamma. Now, if C2 is equal to 0, then we're just going to get the trivial solution, the 0 solution. We don't want that. We want a non-trivial solution. So it means that the square root of sine of the square root of gamma has to be equal to 0. In other words, we have to have that the square root of gamma is going to be equal to pi, 2 pi, 3 pi, so on and so forth. Okay. Or equivalently, gamma is equal to pi squared, 4 pi squared, 9 pi squared, so on and so forth. And then the corresponding eigenfunctions are going to be sine. The corresponding eigenfunctions are going to be sine of k pi x for k equals 1, 2, 3, so on and so forth, like this. Oh, sorry, this is going to be square root of that. No, sorry. I always get this part. I always trip myself up on this part. Okay, square root of gamma is equal to pi, 2 pi, 3 pi, so sine square root of gamma x is going to be k pi x. So this right here, k pi is square root of gamma. Okay, so those are going to be the eigenfunctions in the continuous case. So what we're going to do is, what is that? How does that translate to the discrete case? So let me just write up here, sine of k pi x. So all we're doing now is I'm motivating. So in the homework, I say show that certain things are eigenvectors, and this is the motivation for where that guess came from. Okay, so then we think about what is going to happen in the case of the Poisson matrix. Well, the sample points, the entries of the vectors are going to be our function u sampled at various points. And we know u0 is going to be 0, and m plus 1 is going to be equal to 0 as well. And so we think about it for a second, and we think maybe we're going to have eigenfunctions, a different eigenvector, for every value of k, and then maybe we're going to have something like x here is going to be the point in the grid. Okay, so maybe we're going to have an eigenvector. We're going to have k eigenvectors, k equals 1 to m, and the jth entry of this is going to be sine of k pi xj, where xj is the jth entry, right? So again, if we're thinking about this, if we're thinking about the entries of x as being u evaluated at points on the interval from 0 to 1, then this right here, xj sine of k pi xj. Okay, but remember, if there are m unknowns, this corresponds to m plus 1 subintervals. And so the length of every subinterval is 1 over m plus 1. And so this is sine of k pi, and then j is going to be j over m plus 1. So all this is, if u is the solution to, if u of x is equal to sine of k pi x, let me give it a subscript k. If uk of x is equal to sine of k pi x, all this is right here, this is just equal to uk evaluated at xj, or that's uk evaluated at j over m plus 1. Now here's where things get a little interesting. So if we're in the continuous case, there's infinitely many eigenfunctions, right? As k gets bigger and bigger and bigger, we're going to get a different eigenfunction, and we're just going to have an eigenfunction that's higher frequency. Okay, but here's what happens. There's only going to be m unique eigenvectors in the discrete case. Because what's going to happen, see, the reason that we get multiple things for the continuous case is because for every k we get a different function. Okay, but what happens in the discrete case, if you think about it, as k increases, we're just looking at a fixed number of points. And so if you have a sine function with, say, half the frequency of another sine function, but you're only sampling where the sine function with the lower frequency has zeros, then you can't tell that the sine function with higher frequencies also has zeros. And that's exactly what's happening here. So for example, if this is 1, okay, if we have sine of, let's say, so if we look at sine of pi x would look at something like this. This would be sine of pi x. And then if we look at sine of 2 pi x, we're going to get something like this. Well, no, we're not going to get something like that. Okay, and then we're going to get like this. Now, this function that I just drew, it has zeros here, here, and here, just like the other sine function. Okay, so if we're only sampling here, here, and here, it can't distinguish those two sine functions apart. And that's exactly what's happening here. Okay, maybe I can be even, yeah. Okay, so now for the eigenvectors then, we're going to have different eigenvectors. So this is the my claim. I haven't proven this yet, okay? My claim is that the jth entry of the kth eigenvector is going to be given by this formula here. And this is going to be for k equals 1 up to n. And then what happens when we look at m plus 1? Okay, well, if we look at m plus 1, if k is equal to m plus 1, we're going to have m plus 1 over m plus 1. That's 1 times pi. That's going to be sine of pi times an integer. So sine of any integer multiple of pi is going to be equal to 0. Okay, what about k is equal to m plus 2? Well, if you look at k is equal to m plus 2, we're going to get sine of m plus 2 over m plus 1 pi j. Okay, if I just look at that formula and put k is equal to m plus 2. But notice what this is going to give me. I'm going to have m plus 2. M plus 2 is m plus 1 over m plus 1 plus 1 over m plus 1. So this is m plus 1 over m plus 1 pi plus 1 over m plus 1 pi j, like this. Or this is just going to be sine of j pi over m plus 1 plus pi. Which is essentially, this is just essentially that. Okay? And so, with a minus sign. And so we don't get another eigenvector, we just get a multiple of what we had before. So that's why we only go up to n. Okay, that's one reason. The other reason that I mentioned before is the other reason why we only go up to m. Also from linear algebra, we know that there can only be m eigenvectors, m distinct eigenvectors, or m linearly independent eigenvectors for an m by m matrix. Okay, so how can we verify? So I've maybe given some convincing arguments showing that since the eigenfunctions for the continuous case are a certain thing, then the eigenvectors for the discrete case should be based on that. Okay, but here's what we want to look at. I want to actually show that these are the eigenvectors. So how can we show that these are the eigenvectors? Well, I'm going to show you what to do, and then you're going to do it. I'm going to give you an idea. So what does it mean for this to be the eigenvector? Well, it means that the matrix A times the vector vk is equal to lambda times vk. Okay, so let's think on the left-hand side. What is the top entry? What is the first entry? When I do this matrix vector multiplication, what is the first entry going to be? Well, it's going to be 2 times the first entry of this vector, vk1, 2 minus the second entry of this vector, so minus vk2. Okay, so what is vk1, it's equal to 2 times sine of k pi over n plus 1. We're just doing j is equal to 1. And then we're going to do minus sine k pi 2 over n plus 1. That's when j is equal to 2. Okay. And now what we're going to get, well, what can we do here? Well, you're going to have to use one of these trig identities. Okay, now I'm going to show you how to do it for the 2 minus 1. But for the second entry, it's going to be minus 1 times the first entry plus 2 times the second entry minus the third entry. Anyways, when you do this and rearrange, you're going to get the following. This is going to be equal to 2 times 1 minus cosine of k pi over n plus 1 times the first entry of the kth eigenvector. Okay, so in other words, what this says, for the eigenvector k, this is going to be the corresponding eigenvalue. At least if it's true, if a computation like this is true for j equals 2 through n. So now what this tells us is that our eigenvectors for the Poisson matrix, not for the iteration matrix. I haven't talked about any iteration matrix. This says that our eigenfunction for the Poisson, or our eigenvalues for the Poisson matrix, are 2 times 1 minus cosine of k pi over n plus 1. So let me write that down over here. I'm going to say for A, the Poisson matrix, the kth eigenvalue, lambda k of A, is equal to 2 times 1 minus cosine of k pi over m plus 1. Okay, now let me erase over here. Okay, so now how can we relate this to other eigenvectors, or to eigenvectors of other matrices? So the first thing in the lab or the homework was to show that we cannot just apply the Richardson iteration to AX equals B, that we have to do some preconditioning first. And the reason is, if we look at the spectrum of I minus A. So if we don't precondition our system and just try to apply Richardson's iteration, this is going to be the iteration matrix, I minus A. Okay, and the eigenvalues of I minus A are just going to be 1. So the kth eigenvector here is going to be 1 minus the kth eigenvector there. And what are we going to get? It's going to be 1 minus that. So if I distribute the 2, 1 minus 2, I'm going to have minus 1 plus 2 cosine of k pi over n plus 1. Now here's what happens if k is never actually going to equal m plus 1, right? Because k only goes from 1 to m. But as m gets bigger and bigger and bigger, k over m plus 1 goes to 1. And so for large m, if I look at the nth eigenvector, lambda m of I minus A, it's roughly going to be equal to minus 1. Well, this is roughly going to be cosine of pi, which is minus 1, minus 1, minus 2, which is equal to minus 3. And the absolute value of that is definitely bigger than 1. And so what that shows us then is that unless just a miracle happens, and what it shows is that it's not going to converge there's some initial guess for which it's not going to converge. And essentially what that means is that for any normal starting guess, it's not going to converge, right? Because most of these eigenvalues are going to be negative, and so we're going to get -1 minus -1 plus a positive number, or however you want to look at it. Sorry, -1 plus a negative number, or -1 minus a positive number. Anyways, it's going to be less than -1, in which case the absolute value of the eigenvalue is going to be greater than 1. So the only way for this to converge would somehow be if you could only keep it to the to linear combinations of eigenvectors whose eigenvalues have absolute value less than 1, which is just not something that you can control. So what this says, since the spectral radius is greater than 1, this method does not converge. Okay, or it will almost certainly not converge just if you pick a random starting vector. Okay, but we saw that if we preconditioned it, what we ended up with was an iteration matrix that is 1 minus 1/2 a. 1 minus 1/2 a. Okay, and so now the eigenvalues of 1/2 a are just going to be half of the eigenvalues of a. And what we're going to get here, we're going to get -1 plus, oh wait, sorry, wrong one. What we're going to get here is that the eigenvalues 1/2 a, this 2 goes away, 1 minus 1, we're just going to end up with cosine of k pi over m plus 1. These are the eigenvalues. Okay, now when are we going to get the biggest eigenvalue here? Well, it's either going to be when k is equal to m or when k is equal to 1. So if we sort of think about the unit circle here, when k is equal to 1, the angle is going to be pi over m plus 1. If n is big, it means the angle is going to be very close to 0, and so it's going to be something like this. So cosine, that's how we maximize that there. Okay, right? Cosine is at a maximum when the argument is a multiple of pi, or the absolute value of cosine is at a maximum when the argument, meaning the thing that goes into cosine, is a multiple of pi. And then if we look at m over m plus 1, that's going to be very close to this. So that's how we're going to get the biggest cosines. Okay, so the spectral radius then, for the Jacobian method, I'm going to call it rho sub j. We also use this when we analyze the Gauss-Seidel method, because remember the eigenvalues, the SOR, the eigenvalues for the SOR method, we had that formula to relate them to these eigenvalues. So rho j of this matrix let me just call it T sub j for the iteration matrix, for the Jacobian matrix. T sub j, so the other notation that we call this is T sub j. This is equal to cosine of pi over m plus 1. And that's just because as k goes from 1 to m, we want to see which one of these is going to be the biggest. It's going to be when the argument to cosine is closest to 0 or closest to pi. And that's exactly what we have here, cosine of pi over m plus 1. Okay, so remember what we saw. The error in the kth iteration is equal to rho of t to the power of k times the initial error. Now, here's the thing. We can only make our error. It's only reasonable to try to get our error to within the approximation and the discretization. The approximation and the discretization, if we can solve the discrete problem exactly, the error between that and the actual is going to be on the order of 1 over the number of intervals squared, or the number of entries in the matrix squared. So like 1 over m squared. Okay, that's going to be the order of the error. And so it doesn't make any sense to get anything smaller than that. Okay, in addition, if you sort of think about e sub 0, if you start off with x naught being the initial vector, you can get a rough estimate on e naught, on the magnitude of e naught, and it's going to be roughly 1 over m squared. So what we want to have happen is we want to do k, we want to pick big enough k so that this is going to be less than or equal to 1 over 10m squared times the initial error, like this, where this is m to the minus 2, roughly m to the minus 2. So now what this tells us is we want rho of t, or that should be tj there. I'm just going to call it rho sub j. We want rho sub j to the power of k to be less than or equal to 1 over 10 m squared. Okay, so we want to see what k needs to be. And if we take this and rearrange it, we take logs of both sides, keeping in mind that we're going to have negative logs over here because we're going to get minus 2 over here. Minus 2 to the minus 2 times log of 10m. Then what this tells us is we need to have k times log of rho j to be greater than 2 log 10m. Okay, so let's see how we can estimate this. Well, rho j is this. Rho sub j, the spectral radius for the Jacobian iteration matrix, is cosine of pi over m plus 1. Okay, now let me remind you, let me do a little scratch work over here. I want to estimate this using Taylor's series. And remember, cosine of x is equal to the sum, k equals 0 to infinity, minus 1 to the power of k, x to the 2k, over 2k factorial. Okay, so what this tells us is cosine of pi over m plus 1 is approximately equal to 1 minus pi over m plus 1 squared, and all of this divided by 2. Okay, we're just looking at the first two terms of the Taylor series here. Okay, we can take more terms of the Taylor series, but if you do that, you see it's not gonna change the big O-ness of what we're gonna get here. And then we can also use the fact that log of 1 minus x is equal, not approximately equal to, is equal to minus the sum k equals 1 to infinity x to the power of k over k. And we're going to apply that here. Okay, so I need to rearrange things a little bit. So what we want is we want k to be bigger than 2 times log of 10m divided by log of rho j. This is approximately equal to 2 log of 10m divided by log of 1 minus pi over 2m, pi over m plus 1 squared with the 1/2 there. Okay, but now log of 1 minus x, if I just look at the first term here, it's just going to be the negative of this part. So this then is roughly pi squared, let me write like this, pi over m plus 1, all of this squared with the 1/2. And so if I sort of straighten this out a little bit, we need to have k greater than 4 log of 10m times m plus 1 squared divided by pi squared, and this is O of m squared times log of 10m. Okay, so then the total number of operations to do the Jacobi method for one dimension, well, sparse matrix vector multiplication takes O of m operations, and we have this, so then we get O of m cubed log m operations. Now this is worse than Gaussian elimination. But the awesome thing, and this is something that you will see when you look at the 2D, is that the number of iterations right here, so if I look at in 2 dimensions and I divide the x-axis into m plus 1 subintervals and the y-axis into m plus 1 subintervals, then the number of iterations here is going to stay the same. Okay, so the number of iterations does not scale in this way. The number of iterations needed does not scale up with dimension. It stays constant. Okay, so if I'm looking in, again, 2 dimensions, and I have an m squared by m squared matrix rather than an m by m matrix. So if I have an m squared by m squared matrix, the Jacobi method, even the sort of lame Jacobi method, which is nice but is not the fast method, even the Jacobi method is going to converge, in something like m to the power of 4 times log m iterations. Whereas if we had to use Gaussian elimination, it would be m to the power of 6. And then you can see how this scale is going to 3 dimensions and more. And that's just for the Jacobi method. As you'll see for the SOR method, we're going to have a much better asymptotic here. And that's also going to not grow with dimension. It's only going to depend on how many intervals into which we chop up each subinterval. Okay, so that's it. I know this is a lot, but try to take this and see how you can apply it to the other questions on the homework. This idea is not going to be a huge part of this class. As you can see, it's not really even a huge part of the project, but this is the sort of mathematical analysis of these algorithms that is useful to think about.